Please tell me.
Okay. Anyway, let's balance this reaction, shall we? How's it work? How do I balance this one out? So it takes, we make 2 waters, and to do that, we need 2 hydrogen gases. And I know we wouldn't normally write a 1, but for the purpose of this, I'm going to write a 1. There you go. Okay. Now, in this reaction, then, 2 water molecules decompose, and they give us 2 hydrogen molecules and 1 oxygen molecule, singular.
Why did you do that when you knew the answer?
It was a typo. No, it was a legit typo. I meant to put the S in brackets in all cases, and I didn't. Yes, Londra? If this is about your assignment package, I'm not answering that question. Okay. So this, end of the day. So this allows us to come up with what we call the stoichiometric ratios. And I don't want the words to freak you out. It just means that in this reaction, and you can just look at the reaction and tell me this right away. Put away, please. Okay. I love a good dog picture, but let's focus. So you can tell me this right away. In this reaction, for every 2 water molecules, how many hydrogen molecules are there? 2. Don't overthink it, just molecules. We're just talking about the number in front. Yeah, just 2, right? Does that make sense? Well, we can write that as a ratio. We could say that there are 2, and what unit do we count atoms in? I mean, I could say 2 atoms of H2O, but again, that's useless for us because it's so small. We count atoms in, that's the mass of them, but we're not talking masses here. It's not that there's 2 atomic mass units of water for every 2 moles. We're talking actual atoms. So we have 2 moles of water for every 2 moles of hydrogen gas. And by the way, I know that that's not in lowest terms. You can put it in lowest terms if you want. But for the purpose of chemistry, I actually suggest that you don't. My advice is when you're doing stoichiometry, just take the ratio right from the reaction. It'll make your life easier. Rather than thinking what's lowest terms, what should I divide it by, just put the ratio as it's written in the reaction. And by the way, could I just as easily have said that this is 2 moles of H2 for every 2 moles of water? Yeah. It's interchangeable. It doesn't matter which is on top, which is on bottom. When we go to do problems, we know that when we do dimensional analysis, we're going to put the units the way we want to put them so that they cancel, right? So the stoichiometric ratio can go either way. Doesn't matter which way you write it. And I think I put a little note about that. NB1. Not too bad. So I want you to give me a couple more ratios from this. Write a couple more stoichiometric ratios that you could take away from this reaction. How many moles of blank is equal to how many moles of blank, right? Write a couple more that we can take right from this reaction. Sorry? You could, but don't bother. Like, it would be mathematically correct, but not necessary. Does that make sense? Like, that is totally true, but just my advice is don't go to higher terms, don't go to lower terms. Just read it as it's written here. Okay. Yes, sir? No problem. So what I want to say is this. We read this right from the equation. So we would say, another ratio, what about, let's talk about oxygen. How many oxygens are used in this equation? Good. So we could say 1 mole of oxygen.
That too throws me out.
Yeah, don't let it. Don't let it. That's part of O's formula, right? We're talking about the numbers in front here. How much hydrogen do we use for every mole of oxygen?
2.
Good. So how would I write that?
2 mole.
Yep.
And then H2.
That's right. That's all. And all this tells me is for every 1 mole of oxygen in this reaction, there's 2 moles of hydrogen.
Oh, okay.
Great.
Not so complex.
Yeah, that's it. Yeah, it's not complex at all. Don't let it be complex. Yeah, those look great.
I don't think mine are right then.
Okay, so Kayla and I came up with one here. We said for every 1 mole of oxygen, maybe I'll put the serifs on it so that looks like a 1. For every 1 mole of oxygen, we use 2 moles of hydrogen. Does that make sense? What's another one I could use? Yep.
For every 1 mole of oxygen, there's 2 moles of H2O.
Very good. For every 1 mole of oxygen, there's 2 moles of water. And then obviously, could I flip both of those? Yeah, I'm not going to bother writing them all out. Unless, do you want me to? Is that helpful to see that? Okay. So those can be flipped. You can write them either way. But those are the stoichiometric ratios. And the reason I take this moment to write that out is just to remind you of a skill you're going to use a lot when we go to do dimensional analysis using stoichiometry. So the whole point with stoichiometry is that this reaction tells me that 2 water molecules will break down to give me 2 hydrogen molecules and 1 oxygen molecule. It's just as true then to say that 2 moles of water equal what? Moles of water. That would be 1.2 times 10 to the 24. That's a lot, right? Because remember, each mole is 6.02 times 10 to the 23rd. If I have 2 moles of them, lots and lots of water, what will happen? Good. I'll have 2 moles of hydrogen gas and 1 mole of oxygen gas. But the whole point of a reaction is, maybe I don't want to make 2 moles. Maybe I've got 20 moles of water that I want to react. Well, that's okay, because if I had 20 moles of water, what would I get when I decomposed it? Yeah.
You get 20 hydrogen gas, and then you get 10 oxygen.
Good. 20 and 10 what? I'd get 20, yeah, I'd get 20 moles of hydrogen gas. And I'd get 10 moles of oxygen gas. Good. Very good. Does that make sense? Now, those are nice round numbers. We're going to get, of course, to numbers that aren't as nice and round. What if I had 3.24 times 10 to the negative 7 moles of water? That's okay. We're going to learn how we handle that. And we're going to use dimensional analysis. And we're going to laugh at all the other students elsewhere who are using formulas like m equals n over n and things like that. Oh God, you guys, this is so...
Every time you say stoichi, it sounds a lot more like you are from Australia looking for kangaroos.
Okay.
It does. Like from those cartoons. Every time you say stoichi.
By the way, if you got a puppy and wanted to name it Stoich, it's not a terrible name now, is it? As short for stoichiometry, the dog. It's a good name. I think an underused name, really. You'd probably have the only Stoich the dog on your block.
Probably in the country.
Okay, so let's take a look at this. I want to show you how we can use these stoichiometric ratios to answer a question. So how many moles of hydrogen gas are produced when 2.3 moles of water decompose? The first thing you'll always need is a balanced equation. Now, we already have one for this. But the first thing you will need to do any stoichiometric calculation is a balanced chemical equation. You always need that. So we're going to rewrite this balanced chemical equation. And this is water decomposing. We just did this. So we said liquid water breaks down to form what? Yeah, hydrogen gas and oxygen gas. And what were the numbers that balanced this thing out again? Good, like that. It's an L for liquid. Sorry. Is that better?
Yes. No. Yes.
Yeah, of course. Okay, so with any of these questions, with any time we use dimensional analysis, we start with what we're given. By the way, my answer is going to be in what unit? What am I looking for here? Yeah, how many moles? So my answer is going to be in the unit moles. Hey, since we're looking for moles, what little letter will I use to symbolize what I'm looking for here? Yeah, little n is for number of moles. Oh, I should have used blue. Little n, and I'm looking for how many moles of what? Hydrogen gas. Okay. Does that make sense? That's what we're looking for. Okay. Now, I'm only given one number in this question. So it's obviously what I have to start with. What am I given at the start of this question? Yep.
2.3 times 10 to the negative 3.
So 2.3 times 10 to the negative 3 is the number, but what is it? Moles of water. Okay. Now, that is in moles. So isn't that just the answer to my question? I want moles as the answer, and that's a mole. What's the problem? I want the moles of hydrogen because it's decomposing. Good. So my answer isn't just going to be in moles. Remember, it's going to be in moles of hydrogen. So I want to cancel moles of water and talk about moles of hydrogen. How am I going to do that? I'm going to put moles of water on the bottom because we'll then have moles of water divided by moles of water. And that, of course, just cancels out. And what do I want instead on the top? Moles of hydrogen. Good. Now I need a number to put in there. Where do I look to find the relationship between how many moles of hydrogen and how many moles of water? Where's the 2? Okay, so how many moles of hydrogen are used in the equation? 2. How many moles of water are used in the equation? Yeah, this is going to be some boring math, but that's okay. It's a good first learner. In fact, it's very intentionally chosen. Very intentionally chosen as a nice, simple equation. So since moles of water cancels with moles of water, what will be the unit of my answer here? Moles of hydrogen gas. Good. And now we need to get the number. Now, this is easy because anything times 2 and then divided by 2 is just going to be, well, whatever we started with. Good. So the number here will be 2.3 times 10 to the negative 3 moles of hydrogen. By the way, we could have told that just by looking at the equation, right? Right? I mean, we can intuitively know for every 2 moles of water, we get 2 moles of hydrogen, right? Okay, so we could have easily said, okay, if instead of 2 moles, it was 2.3 moles, then for every 2.3 moles of water, we'd get 2.3 moles of hydrogen, right? And then we could have said, well, then for every 2.3 times 10 to the negative 3 moles of water, we should get 2.3 times 10 to the negative 3 moles of hydrogen, right? Yeah, okay, so that's a boring question. But does everyone see the math we did? It's not enough just to be able to intuit it. We need to make sure we can make it work mathematically. And dimensional analysis tells us that if we carefully write our units out and make sure the numbers come in correctly, that we're good. I want to take a moment and just highlight these numbers so we know where they came from. This 2 moles of hydrogen, where did I get that number? From the equation, specifically which number in this equation? This one? Great. That's right. That number comes from the balanced chemical equation. Likewise, down here, we have 2 moles of water. Where did that number come from? Yeah, it came from here. You know, I'd make a comment about my highlighters, but I feel like Jade would point out that, oh, you say that all the time. But, you know, they just look so dull up there, and they look so lovely and vibrant on my screen. I know. I don't know what to tell you. Okay. You know, it's a contrast issue, and if I can make them look better on the screen, but then the screen just gets dimmer. It's harder to see, and in the end, the trade-off is worth it because I like to be able to have the lights on and the windows open. So it's fine. It's okay. So just keep in mind these numbers, which are the stoichiometric ratios. And you know what? Just for you guys, stoic ratios come from the balanced chemical equation? I'm using all the short forms here. Look at that. Equin, the balanced chemical equation. Good. The stoichios. I kind of like that, actually.
Or did you show him?
Skid it up. Okay. That was some jazz. You're welcome. Let's go on to the next page. Nope. Is it about this? Nope.
Nope.
Okay. So, shh. Now we're going to get to an actual difficult question. All right? This question is challenging. This question is going to take us some time to work. In fact, we got to break this down. How many moles of oxygen gas are produced if 3.4 times 10 to the 3 grams of lithium oxide are decomposed? Oh, man. Let's look at this question right now. It involves naming. It involves predicting a chemical equation. You're going to have to find the molar mass of things. You're going to have to convert from grams to moles. And then you're going to have to do the stoichiometry, all in one question. Every unit you've done in this course, all in one question. And by the way, this is a straightforward question. They're a lot trickier than this. Now, you may think that sounds intimidating. It's actually the exact opposite. Here's the nice thing. Every time you do a question in chemistry class, you're doing exam review. Every single question we do, we're getting ready for the exam because you're practicing all of your previous units all the time. It's kind of nice, right? It's not like biology where you learn unit 1 and then you never think about unit 1 again until 2 days before the exam when you go, I said I was going to start studying for this weeks ago. Oh my God, I'm out of control. And then you like stay up for 4 days straight and like, and you're like twitching. And then, like me, you realize you've skipped the exam. Not unlike the concert I accidentally skipped last night. When last night at about 9 p.m. I was checking my email and I got, reminder, you have an event in Toronto. I was like, I just paid $200 for a concert I didn't go to. That's frustrating. Yeah, I was pretty upset. I forgot all about it. I bought the tickets way back in like April and then just didn't think that.
What was the band?
That was a different show, actually. It was Bruce Coburn, who's one of my favorite guitar players. So I'm pretty bummed out. Very disappointed in myself. But these things happen. This is the kind of thing I do. I do this kind of thing a lot.
You were busy with stoichiometry. It's like, oh, yeah.
It was election night. I was sidetracked. I don't know. I don't know what to tell you.
Got better things to do.
But I'll tell you, I like guitar a lot more than I like numbers.
2 hours before church, we have the time for it. Go in Toronto. It's a reminder. It took me 90 to go to it. Why would you set it when you would be?
I didn't set a reminder. Like Ticketmaster sends you a reminder. And it was just, it went to my junk mail. And when I checked my junk, no, they sent it the day before, but it was in my junk mail. When I checked my junk mail, it was like, oh, there's an event reminder. That would have been really useful if I'd, read it in time to be reminded. Anyway, these things happen. But it was frustrating. I burned out my 2017 concert budget for those tickets and then didn't even go to the concert. Anyway, let's take a look at this. So the first thing we need, I said last question, the first thing you need to do any question like this is a balanced chemical equation. So we got to do it. So this starts with what? What's the first thing in this? Well, oxygen is what we're looking for, and that's what our answer is going to be about. Our answer is going to be about moles of oxygen, right? But the actual reaction, lithium oxide, and what's it doing? Decomposing. Okay, so the first thing we need is a formula for lithium oxide. How do we find the formula of lithium oxide again? Balance the charges. So lithium, what charge does it take? Yep, 1. And oxygen takes what charge? 5, 4, 3. I'm going to keep going. 2, 1, 0. -1. -2, -3, -4, -5. Okay, guys, it's one of those. Go. -2, correct. Good. Okay. So There we go. What's the formula then for lithium oxide? Lithium 2, oxygen 1. Now, of course, would the name of that be lithium 2 oxide? No. Its name would just be what? Lithium oxide. Good. Okay, so we start with lithium oxide. And what is it doing? Decomposing. What are we going to get when it breaks down? That's a solid. You tell me. It's a decomposition reaction. You guys have done decomposition reactions. Lithium.
Plus O2.
Oh, and you didn't even forget the 2. You're so good. That's great. And what state of matter? What state of matter is O2? It's a gas. Good. Okay. Good. I'm good to go. All right. Let's get going.
You're going too fast.
Well, what? I'm good. I've got a chemical equation. It's like that.
It's not balanced.
Okay. Okay. There we go. And we're balanced. Let's go. Yes, we are. 2 lithium, 2 lithium. We're good.
You need a 2 on the other side. I
think we should go
We need
through
2 on the
with
other side.
I need 2 here.
And then a 2 on the lithium.
Okay.
That's it. Oh, then a 4 on that.
I need 4.
A 4 on this. That's what you said. You said, and then a 4 on that. What am I? Oh.
Oh, 4 goes on the lithium.
Yeah, good. Why is it 4? Very good. Because this is 2 Li. 2 times 2 is 4. So we have 4 lithiums over here. So we need 4 lithiums over there. Okay, good. So now we have a balanced chemical equation. All right. Now, let's take a moment and we'll get started. We're going to do some stoichiometry here. And whenever I do stoichiometry, and I want you to get in the habit of doing the same, we set up, first thing we put is our given. And we only have one piece of given information in this question. What is it? Yeah, specifically, how many of them? Okay, so we start with 3.4 times 10 to the power of 3 grams of lithium oxide. I did. There we go. Okay, now, here's where you have to sort of map a question out. You can never go from grams of one thing directly to moles of a different thing. Does that make sense? So before we can talk about moles of oxygen, which is going to be the answer, I have to be talking about moles of lithium oxide. Does that make sense? First, we have to start talking about moles in general. And then once we've done that, we can figure out using the balanced equation, moles of one thing to moles of another. So I don't want to be talking about grams at all. Grams is not useful for this question because reactions don't happen in masses, they happen in numbers, right? Individual atoms smashing into individual atoms. So what do I have to cancel here? Yeah, we're going to cancel grams of lithium oxide. And what do I want as my unit? Moles of lithium oxide. And listen, we're not going to put any numbers in yet. We're going to put no numbers into this. We're just going to set the units up. If I stopped calculating now, what would I know? Good. But we're going to do this all in one step. Dimensional analysis doesn't have to be a one fraction. We can multiply by another fraction. Yeah, we can do this. Because now, I don't want to know how many moles of lithium oxide. Right? What do I want to know to have answered the question? I want to know how many moles of oxygen. I don't want to know how many moles of lithium oxide. And listen, this is going to take some practice. Don't worry, we're going to spend days doing this. And now, moles of lithium oxide will cancel with moles of lithium oxide, and I'll be left with moles of oxygen. Good. Okay, now, listen. Now we have to put the numbers in. Now we have to put the numbers in. One of these we already have the work for. One we're going to have to do more work for. Which one of these do we already have the information up on the screen for? Do I know how many grams are in how many moles of lithium oxide right now? No, right? There's nothing in the equation that will tell me how many moles of lithium oxide give me how many grams of lithium oxide. So I can't do that yet. We're going to have to do some work for that. But what do I know?
We know how many oxygens go into lithium oxide.
Yeah. So here, oh, didn't mean to do that. Here, we can look at the balanced chemical equation. From the balanced chemical equation, in this reaction, how many moles of oxygen do we use? 1. We use 1 mole of oxygen. I'm going to color code that so we know where that number came from. And what about lithium oxide? How many moles of that do we use? 2. And we got that from here. Does that make sense?
That's the whole yes. Here's the number.
Is that comfortable where we're getting that information? When we go from moles to moles, that's always from the balanced chemical equation. So when we go from moles of one thing to moles of something else, that always comes from the balanced chemical equation. That is stoichiometry. That's what today's lesson is about. So from moles of one thing to moles of something else, this is just a reminder. That is stoichiometry. That's what stoichiometry is. And to do that, we always use the balanced equation. I mean, it already says that on the previous page, but it's never a bad idea to write that out again.
Year 2 looks like the Greek letter alphabet.
Yeah, kind of, a little bit. Okay, but now this first one, we've already done in the previous lesson. How do I know how to go from grams to moles? What do I need for that? We did a whole lesson about it.
Well, when you get the same amount of moles as you can for empty milligrams, so when I do like 2 moles and 2 oxygen?
Yep, but we're not going from moles to moles. What I need to go here is grams to moles. I don't know the second one. All I've been given is a mass. That's the whole point. And mass, you can't go from mass to mass. Just the unit. We still need numbers for all of these fractions, Alondra. Every fraction has to have numbers in it that are true. So look, let's pretend we weren't doing that. Let's pretend this was the whole question. What would I do? All right, I want you to pretend that that last bit isn't there at all. How do I do this part of the question? Okay, 1 mole of lithium oxide is going to weigh how much? How do I know? What do I have to do? From the periodic table. Good, we have to find the molar weight. We have to find the molar mass using the periodic table. Your thinking, by the way, Alondra, is good. Like that we could work on it mathematically, but you have to remember that for dimensional analysis to work, every one of those fractions has to have true numbers in it, and every one of those fractions is going to have a key. Whenever it's going from moles of one thing to moles of something else, if it's a fraction with moles and moles, that comes from the equation. But if it's a fraction relating grams to moles, that has to be a molar mass. And the only way to do that is using the periodic table. So let's find the molar mass here. What is the molar mass of lithium-2 oxide? Well, it's going to be 2 times the molar mass of lithium, right? Plus the molar mass of oxygen. So what are the actual numbers for that? How much does lithium weigh? Yeah. Okay, do you mind just giving me the numbers in the middle too, just so I can write them down? 6.9412, and that's grams per mole. Very good. And then we have to add to that oxygen, and that's what, 15.9994 grams per mole. Great. And Ruby, you've got the final?
Yes.
Great. Great. What is it? 29.8818. And the unit on that, of course, is grams per mole. Good. By the way, you do not need to show this in 3 steps every time. I'm showing it in 3 steps so that when you come back and look at my note after, you can be like, where did that number come from? Does that make sense? But especially once we get later on in this course, you're going to be finding lots of molar masses. We're not always going to write it out in 3 steps like that. That would be cumbersome. But now we know. Now we know that 1 mole of lithium oxide weighs how much? 29.8818 grams per mole. So 29 point, what is it? 8818? Now, I want you to take special note. In the balanced chemical equation, how many moles of lithium oxide do we use? 2. Having said that, in this step, where we're converting from grams to moles, how many moles did I put up top? That's because this fraction has nothing to do with the balanced chemical equation. This fraction is strictly the molar mass. That's what this fraction is. It tells me that 1 mole of this stuff weighs 29.8818 grams. So this whole number, which I'm going to highlight in blue, is our molar mass calculation. That's where that number came from. Does that make sense? Again, I promise these get easier the more you do with them. We're going to do 1 more together, and then we're just going to spend days practicing. But when we actually do this calculation, what do we get? By the way, how do I punch this into my calculator? I would do 3.4 times 10 to the 3, and then times 1 divided by, great, and then? Good, very good. You just go along. Some people,
Do you need brackets?
if you do times divide, you do not need brackets. You can just go. You can use brackets, like it won't be wrong, but you don't have to. Yep. What did you get? 56.8908. And what unit is that? Moles of oxygen. Okay. Great. Everyone do that. Make sure they get the same. But on the face of it, that looks very reasonable to me. Now, I do want to talk about something. What do I want to talk about? Hey, what did we say green was the official color of? Sig figs. How many sig figs do we have here? 2 sig figs. How many sig figs do we have here? Well, this one matters. How many? 6 sig figs. And then, oh no, this is only 1. That's going to screw my answer up. Okay, don't yell at me. And this, of course, is also infinite. And this, of course, is infinite. Fine, I won't have fun anymore. So how many significant digits should my answer have? 2. So what should the answer be in the end?
57.
Very good. 57 moles of O2. By the way, what small letter do we use since we're finding the number of moles? What is it? N, great, and specifically N of O2. By the way, do you see why writing full and complete units is a must-do for this kind of chemistry? You can't get lazy with your units because a mole of lithium oxide is different than a mole of oxygen. They're not the same thing.
It's not like math, so it's just a number.
That's right. This is math contextualized, and that context is important. Yeah. Okay, ready? This next question is even more tricky. And I want to draw you a little map just here. And every once in a while, we're going to refer back to this map because I want you to know that finding out how many moles of something we have is this central and important thing. What letter do we use for number of moles, of course? And we measure that in moles. Okay. That is a central thing. Because if you know that, you could figure out, if you wanted to, number of particles. We will almost never do that because it's really useless, right? Knowing exactly the actual number of atoms we have. But if we wanted to, we could do that, right? What would you just have to know? You know that 1 mole is what? How many particles in a mole? That's right, that's Avogadro's number, right? And so if we wanted to, if we know how many moles, we can figure out how many particles. That's one we will do very rarely, but you can do it. But if I know how many moles of something I have, what else can I figure out? And that can go back and forth, of course. If you know how many particles, you can figure out how many moles. I can use the molar mass to figure out the, if I know how many moles I have, I can figure out how many grams I have. I can figure out the mass, right? Oh, battery low. This is why we're supposed to charge you the night before, computer. I just want to show, sometimes some people are really helped by having kind of a map of what they can learn if they know something. So if we know how many moles, we can also figure out the mass. What letter do we use for mass? That's what we use for molar mass. Little m for mass. Again, this is why we don't use equations, because they're deadly. But still, and to do that, all we need to know is that there are blank grams in however many moles, right? And we call that just the molar mass. If we know the molar mass, we can go back and forth. And then the other thing I'd say is, we can also figure out, whoa. We can also figure out moles of something else. In other words, if I know how many moles of oxygen I have, I can figure out moles of hydrogen. Yeah, you'll have, don't worry, I will leave this up. And again, this is just kind of a quick little reminder. It's helpful to us. Sometimes I will map out a question like this before I do any math if we get to really complicated ones. In fact, the next question I'm going to map out before we do. And we do that using the stoichiometric ratios. So there we would set up a ratio in our dimensional analysis where we say moles of this thing and moles of that thing. Does that make sense? So far, those are the 3 tools we have. We can go from particles to moles and moles to particle, back and forth. We can go from moles to mass and mass to moles, back and forth. And we can go from moles of one thing to moles of something else, back and forth. By the time we're done the course, you'll have a few more of these. This map will get a bit more interesting. But it's already pretty interesting.
Is that going to be an assignment to make a map?
No. Would you like it to be?
Yeah.
I could come up with something. I don't do a lot of, that's one thing, I mean, maybe you guys have caught on, maybe you haven't. I'm a little on the boring side, and I don't do a lot of these, like, build me this thing, like using paper mache projects. I tend to avoid those because I'm just naturally adverse to anything fun or interesting.
But those are so fancy.
You know, here's the thing for me. This is me being curmudgeon-y, it's me being whatever, miserable. That's how I feel about like demos like elephant toothpaste. And you're like, oh, that's cool, because it like bubbles up. And it's like, okay, what'd you learn? Well, it bubbles up and it was cool. And that offends me as a chemist. I'm not a chemist, I'm a chemistry enthusiast. But still, as a chemistry enthusiast, it offends me, yes.
But if you make the map, it can help us later on.
Yeah, no, the map, on the other hand, I think is useful. So here's what I want to say. Let's look at this question. What information am I given? So 3.2 grams of solid copper. And what does the question want me to tell you as an answer? Good. Grams of metal oxide is going to be the answer. Hey, what's the first thing we're going to need to do this question? Okay, so it's balanced chemical equation. What is it? What do I start with? It tells you right here. I'm taking 3.2 grams of. Great, so what is that? Cu. And what state of matter is it? Great. What am I reacting it with? Oxygen. By the way, what do I mean by excess? No, I don't mean like left. I don't mean that the oxygen already is left over. What I mean is there will be leftovers. I've got some copper, and then I've got all the oxygen I need and plenty more. Does that make sense? Later on, we're going to talk about situations where you actually have given masses of two things. You have to figure out which one runs out. It's kind of nasty, right? But for this question, we're saying you've got this amount of copper and then all the oxygen you need and more. That's what the word excess means. Would you like me to make a little note about that, or is that comfortable? We're fine? Okay. So oxygen gas. And what's that going to form? Sorry? Two of them? Okay. Fine. Because it is a made-up word, diatomic. Good. Though you're right. It's a Hofbrinkel, but specifically it's diatomic. Now, this, by the way, how many possible answers are there to this? This lab, which one do we get? Copper 1 oxide or copper 2 oxide? Yeah, it's the copper 2 oxide. And what's the formula of that? Copper takes a charge of 2 plus in copper 2, and oxygen takes a charge of 2 minus. So the formula of the product will be? CuO. Very good. By the way, if I gave you this question without it being something we'd done in the lab, you'd have to say, hey, which product should I use? And I would have to give you that information. Does that make sense? You have to know that. So here we go. Okay. We're done. We can move on. Fine. What do I need to do? Like that. Okay. I like that. Okay, here's where I want to draw a map. Some of you may find this technique helpful. I find it helpful. Some of you may find this more confusing, in which case, don't do it. Some of you may find this irritating, in which case, don't do it. I sometimes like to map a question out. So let me do that. What information do we start with here? Again, I'm only given one actual piece of information. Yep. What information am I given? Good. So the information I'm going to start with is mass of copper. Does that make sense? And I can even put the number here if I want, 3.2 grams. But I just kind of have to draw a map for myself. From a mass of copper, let's go back to our map. If I know the mass, what's the only other thing I can find? And the number of moles of the same thing. Does that make sense? Can I get from mass of one thing to number of moles of something else in one step? No, that'd be nice, but I can't. So I'm going to have to go from mass of copper to what? What's the next step of this equation going to be? Yeah, the number of moles of copper. All right, and that will be in moles of Cu. Obviously, I don't know that number yet, but that's what I'm going to have to figure out. Now, what is the question asking me to find? I highlighted it in green. Grams of. Okay, great. Now, can I go from moles of one thing to grams of something else? Can I go from moles of this to grams of that? No, so I'm going to have to go from moles of one thing to moles of the other thing. So when I want to go from one compound, from talking about copper to talking about copper oxide, I can only do that if the unit I'm talking about is moles. Does that make sense? That's the only time we can do that conversion, because we have to do stoichiometry, and stoichiometry is based on the number of things. So I can go from the moles of copper to the moles of, what's the question you want to know about? The metal oxide, and in this case, the metal oxide is copper oxide. Good, CuO. And now that I know how many moles of copper oxide I have, well, now you can always go from moles to, I can go from moles to number of particles. Does the question want to know how many particles? No. I could go from moles of copper oxide to moles of something else, but I want to talk about copper oxide. I can go from moles of copper oxide to the mass of copper oxide. Good. Now again, you may not find this diagram particularly helpful, but for me, it helps me keep track of what I'm doing. Does that make sense? It shows me what I'm starting with, what I'm going to end with, and what my steps are in the middle. Does that make sense? And I can start to put some information in here too before I do any math. To go from grams to moles, what do I need to know? To go from grams of copper to moles of copper, what number am I going to need? The atomic mass. So what's the molar mass of copper? I can throw it in here. Again, you don't have to, but I can. So off the periodic table, what's copper weigh? 63.546, I think, grams per mole. Yeah, so I'm not going to show them all in here, but if you draw a map like this, you can even put the numbers you're going to need in the map, sort of over the arrows. Does that make sense? Now again, I will never tell you you have to draw a map, never something like that, but for me, that's a helpful tool just to help me arrange my thinking. Some people like to just dive right into the dimensional analysis. They just go, hey, I can write the units out, I can cancel the units, that's comfortable for me. Great, nothing wrong with that. Whatever works for you, all right? And we're gonna do so much practice, you'll figure out what works for you. So now, let's get going with the dimensional analysis. What is the information I'm given to start with? Very good. So we start with 3.2 grams of copper. And my first step is going to be what? I don't want grams of copper. I know that's going to get canceled. What do I want? Moles of copper. Okay, and we can throw those numbers in now. How many moles are in how many grams of copper? Or how many grams are in how many moles? 1 mole of copper. It weighs how much? 63.546 grams. Good. And I'm just going to put a little reminder here. That is the molar mass. All right? How do we convert from moles to grams? We have to know the molar mass. Okay, if I were to stop now, if I stopped doing this question now, what would I know? Good. I'd know how many moles of copper. Is that what the question asked me? So I got to keep going. What's my next step going to be? Good. We don't want to talk about copper. We want to talk about copper oxide. In fact, I want grams of copper oxide, but I can't do that directly. So I've got to do this intermediate step. So we're going to not talk about moles of copper. We're instead going to talk about moles of copper oxide. And what numbers go in there? 2 moles of copper. And up top, how many moles of copper oxide? 2. So that's an easy one. Right? That just cancels itself out. I'm going to highlight there just so we know where those numbers came from. Okay, what units cancel here? With? Good. If I were to stop calculating now, what would I know? The moles of copper oxide. Is that what the question asks me to find? No, so I need to keep going. I don't want moles of copper oxide. What do I want? Grams of copper oxide is correct. Good. And now, where am I going to get that number? What do I have to do? Anytime we go from grams to moles, we're going to look at the periodic table, and we're going to find the molar mass. So the molar mass of copper oxide, how much does copper weigh again? 63.546. And how much does oxygen weigh? 9994. And those are both grams per mole, of course. You can't see, but I wrote it here. Of course I wrote it here. There it is. I mean, it should be on the order of 79 point what? 0.545? Someone do that? Great. Is everyone comfortable with that? How we got that? Okay. So I'm going to say that and that. Right? What do you mean no? I like it. I put it. I wrote it. I'm the teacher. Respect my authority. 2 grams. Okay. 2 grams. So 2 grams of copper oxide is the mass of 79.545 moles. Okay, that's wrong. Okay, what should I have done? Okay, so what goes up here? 79.545. And then down here, that's how much 2 moles of copper oxide weighs, right? But there's a 2 in the balanced chemical equation. That's right. We're talking about the molar mass here. That's got to be a 1. When we're talking about the molar mass, that's always the mass of 1 mole. By the way, that will be your most common mistake. I guarantee it. It's always the most common mistake. People forget and they put how many moles from the equation go here. That is the natural mistake we make at first. That's okay. It means you're paying attention. It means you're looking at the equation, which is good. It just means we have to clear your thinking out. It's, as mistakes go, we like that mistake. It means you're thinking. It means you're thinking stoichiometrically. Okay? Now what will cancel? Moles of copper oxide will cancel with, and I'll be left with grams of copper oxide. Cool. So is that complicated? It is. But in a couple of days, I will show you how I was taught to do this in high school. And it's so many steps and chaos, and you have to keep equations straight. And it's like, you ever do those kinds of tests, especially in physics, where you're like dividing your page up and you're always like drawing a line and saying like, this calculation goes over here, and this one goes over there, and this one goes over here. Dimensional analysis strips all that away because we do one calculation, and we just keep going. We keep adding multiplication lines until we get what we want. Does it take a bit of practice? Absolutely. It definitely takes practice to get good at it. But once you get good at it, it's amazing how efficient and how effective that is. And the nice thing is, how many times do you have to pick up your calculator and do a calculation? Once. Now, maybe twice if you also had to figure out the molar masses, right? I mean, I have seen kids who get really intense, and in a bracket up here, they just write the addition. So they really can do it like in one step. That, to me, is a little... That's extreme. That's intense. But it does work. You can do it as long as you're careful with your brackets. I think that's kind of nuts. So I wouldn't do that personally. But you be you, and I'll be me. All right, so can we actually do this calculation? It should be on the order of, like, I'm going to say 3.8 to 4.2, somewhere in there. What are we getting? 4.005? 4.006. And what unit will that be? Grams of copper oxide. You know what's funny? I don't know what it is. When I'm teaching math and I go to do math in my head, I blither and bumble and always get wrong. Then I teach chemistry and I go to do math in my head and I'm always really close. But like, math is math, and I don't know why that is. I don't know why in this context I can be like, yeah, okay, it's super. Yeah, I guess I've done a lot of this. Okay, and we are done, and that's a good final answer that will get me full marks.
You have a party.
I host a Christmas party every year. So I'm glad to see that Brianna's coming. So that's a good answer, and we're done, and we're good. I'm done.
Are we coming to your party?
Yeah, no. Yeah, that's what I do. I invite a lot of students to my Christmas. I mean, for the record, I'm quite boring. Like, you would see nothing at my Christmas party that would shock and scandalize you. But you know what I'm not thinking on the first day of my Christmas holiday? How can I extend my time seeing students? It's just not my main focus.
One of my teachers at the end of the year actually had a pool party and invited all their students.
Can I say, I have always, when I teach graduates, like if I teach, like if you're in my grade 12 chemistry class last year, I always at the end of a semester with graduating students do a little like, for anyone who's interested, have like a little finishing chemistry up dinner, but not at my house.
Just, I don't want you to know.
You're not invited to my home. I'm sorry. Like, listen, if you're like if you're in a car accident and it happens to be near my house, like, sure, come use my phone. But failing that, no. Okay. What do I need to do with this question that I have not? Sig figs. Good. The last thing we always look at, sig figs. So how many here? Okay. I will just do the whole numbers. This one is Sank and 5. So the answer must be. Oh, okay. So the.
I mean, like the answer is 4.
Oh yeah. Well, specifically 4.0. I thought you were being snarky. I thought you were doing what Brody always does, where the answer to every question is 47. Which is actually it's charming in its own right. I know. I should start making all the practice questions so the answer is 47. That's actually a good idea. Oh, I'm on it. I'm totally doing it. Okay. Now the bell's going. Let me just finish this sentence here.
Like the last question has to be the
Yeah, I like it. I had a high school teacher once who gave us a multiple choice test with 25 questions. The first 24 were C, and then the last one was A, and I thought that was incredibly funny. Okay, so what we have just done, and it's easy to lose context because we did a bunch of math, is pretty amazing. I've told you that if you take 3.2 grams of solid copper and you react it with oxygen, and there's lots of oxygen, you'll end up with 4 grams exactly of copper oxide. That's actually pretty amazing. All right, that is some advanced chemistry we've just done. We've now made a prediction. And we can test that prediction. Have a wonderful day. Be kind to one another. Don't do anything Taylor wouldn't do.
I get to thank you for that.
We will see you tomorrow.
now.
Sorry?
These packages right now.
If you have finished your assignment, I will happily take it.